history to support closure by natural attenuation. Chuck, David?
Great, thanks, Andrea. This is Chuck Newell.
And David Adamson. We're from GSI Environmental.
And today we're talking about our ESTCP project, determining source attenuation history to support closure by natural attenuation. So sort of an unusual title. It's got the word history in it. A lot of times we do a lot of technical stuff, but so what's the story behind this? And just briefly is we had been doing a lot of work in the area of matrix diffusion, and in some cases that's bad news. It's hard to get those contaminants out of these low permeability zones. And so we were wondering, is there anything useful about this? And there certainly is. We realized that in some of these low permeability zones, these clays and silts, that there's information, almost like tree rings, and you could go back in and understand how these different source zones may be changing over time, and potentially the value is you could say, well, if you knew that this source was attenuating over a span of 15 or 20 or 30 years, you could make this case it's probably going to keep on doing similar type attenuation. This has been going on for a long time, and help you close that site. And we got into it. We realized there were some researchers that had already done some work on this, starting almost, how long ago, Dave?
About 20 years.
And so then we picked it up and then formed a team to do this. So if we go to the next slide, who's on the team? Mm-hmm.
Right, and so this is a joint project between GSI, Chuck and I have already introduced ourselves, and the University of Guelph, specifically Beth Parker and Steve Chapman there. And so those are the primary PIs, and then we had a lot of help on this project. Names there are on the right-hand side. We'd like to highlight Mike Singletary at NAVFAC, who was very helpful in terms of helping us get this project moving.
So if we move on to the third slide, where we're talking about the technical objectives, we had 3 of them. And the first, determine if high-resolution sampling of these low permeability zones can reveal this accurate source loading history at sites. Number 2 is conduct this field demonstration to sort of go through this whole process. We're going to collect the data and develop this way to process it. So there's a spreadsheet tool in here to help you do this, and then actually do this at 1 or 2 sites. And then third is develop this software tool that people can download. It will be funded for by ESTCP, so it's free. And then people can do this at their sites, apply it, develop their own source loading histories. So that's sort of the text of it, but I'm more of a conceptual picture guy. So what's the cartoon look like, Dave?
Okay, so we developed this cartoon that's on slide 4 to sort of provide an overview of what we're talking about. So this is 2 panels. One at a time in the past, the left panel saying, say in the 1970s, maybe shortly after release, and then the panel on the right is what conditions you might see now. So if you look at this left-hand panel, it's got 2 layers, a transmissive zone overlying a low permeability zone, like a clay or silt, some type of tight formation. The transmissive zone has this source, this red source up in here that feeds into a plume. If you were to take soil cores in that low permeability zone underneath both the source and the plume, you'd see these sort of characteristic concentration with depth profiles that are what we call diffusion profiles. Let me highlight with this little highlighter there. So that's the data from the low K zone, these cores. And the profile concentration with depth would be basically highest at the interface and decreasing downwards. So that's based on the diffusion gradient. If mass wants to go from high to low concentrations. And it would look sort of like that both at the source and the down gradient plume. So if you then were to come back, say 40 years later, so that's the right-hand panel, and take cores in those same locations, maybe after the source has done some sort of attenuation and the down gradient plume is attenuated, you might see a different pattern in that soil core. So here's the one in the source where the concentration peak is actually some distance into that low K zone. And these are characteristic profiles of an attenuation of concentration over time in the overlying transmissive zone. And you see the same profile then at the down gradient plume. So what we're trying to do is take this information from the core and relate it to what we would expect to have happened, that C versus T, or the source history over time at that particular site.
And 2 quick points, Dave, is on that right-hand panel, you see both of those concentration versus depth profile. That we call those the shark fins.
Yeah, that's a good way to sort of think about it, yeah.
So a shark fin means that that concentration right above that sampling point, the concentration in that transmissive zone has gone down significantly over time.
Right. You've essentially switched the diffusion gradient, the concentration gradient, such that mass is then moving outward so that the peak is down there at some point in the locate zone.
And maybe just the second point, and this is, I think, was confusing as we wrote it up, and is that the title of the whole thing is Source Attenuation History, but we actually do this both in the source zone but also downgrading in the plume. And our conceptual model is that you do it downgrading the plume, you're getting a lot of the source history signal. Maybe there's some other plume dynamics going on, but that's really what you can do this in the source or the plume, or in our case, do both.
Great.
So now we've got 3 slides about our actual performance objectives. ESTCP wants you to say this is the bar we're going to try to reach, and at the end of the day, they say, have you done this or not? So these are our criteria that we constructed. Number 1 is more or less the accuracy. Can we actually, the best that we can determine, really reconstruct this source history and get this, as Dr. Parker says, reconstruct the style of the source. Is it one that's been more or less constant over time, or is it actually been declining? Can we see that? Number 2 is precision. Is if we do multiple samples here, can we get these source histories being sort of the same answer by doing it over again? Mm-hmm.
The third and fourth quantitative performance objectives, then number 3 is sensitivity. So also, if you may have some uncertainty in the input parameters that you're using for this type of a model, maybe you don't know the porosity with that much certainty, how much does changing that by a small amount or a small amount or a big amount change the type of answer you get in terms of your model prediction? Then finally, number 4 was basically a comparison of methods, trying to just take a look at the sort of data that you get out of this high-resolution field investigation, what kind of trends you see in terms of various steps of sampling and analysis.
Do you have to use university lab all the time, or can you send it to your common lab? That was some of the questions we wanted to answer.
Sure.
And then this last one is ease of use. Just feedback from the field personnel. Can you do these methods? Is it something that's within our capabilities of doing it? Is the software okay? Stuff like that. So that's the third slide. So we have really a couple of end products. We've got 4 slides on that. What's really the first end product of the proposal?
Well, we've already mentioned this, and the first one under there is basically this tool. It's a software tool that allows people to do this on their own. It's a relatively straightforward tool, and we'll show some screens from that here in just a second. But it allows people to kind of to play around with this, or to take data that they have from their actual site and get answers from it. And that's basically facilitated by the second end product, which is a user's guide for the tool. So it's not only showing sort of how to use the software, but how to get the data that allows you to use the software, how to sort of conduct a high-resolution site characterization that would feed into this sort of a characterization approach.
And a lot of those methods are coming from University of Guelph, right?
Right. They've been one of the real leaders in sort of adopting and promoting this style of site characterization.
So what's the top picture in the middle picture there?
The top picture is one of the sampling devices, just a core sampling, subsampling device for extruding samples. The second one is I like to highlight these, I guess. Basically, a set of cores, 5-foot cores taken from one of the locations that we at our demonstration site. So each of those little holes in there is a soil subsample that we took. And then finally, the bottom picture is just preserving that in methanol in the field before sending it off to the lab for analysis.
Spacing on those holes, so they're like every 4 inches?
Every 4 to 6 inches is pretty much what we use at this site.
Okay. Mm-hmm. Let's take a quick look at the simple spreadsheet model, and this is the whole thing, what it looks like if you had collected this data from some of these cores, and this is concentration versus depth, penetration depth into a clay, then this is what you have to throw in there to reconstruct this source history. Hard to see here. Let's blow this up into the left panel.
The left panel is basically your input screen, and again, this is just a single screen is all it takes to sort of access this thing and interface with this, so everything you need is on that one screen. The left-hand side is all the input data, so you're working with hydrogeologic parameters, in this case, things like porosity and soil density, the type of compound, COC that you're working with, the fraction of organic carbon, constituent half-life is built into this, so in case you wanted to incorporate degradation. And then the primary data input then is this high-resolution CVOC data from soil cores in the low-K zone. So taking that soil core data, concentration with depth, and entering it into this side.
And the original vision was then we're going to hit this button and Excel's goal seek was going to optimize all this stuff and sort of tell you what this answer is. And we tested it, and goal seek in some cases did okay, but other cases had a mind of its own. So we said we got to replace this with a better computer and better goal seek, and that's just the human mind itself, right? And so on this right-hand side, you've got this stuff in there, and we want you to move these slider buttons, and each slider button says, what's the concentration in 1975? What's the concentration in 1980? And it's your job to get this curve to match your data point. And so this is something that just takes a couple minutes. How long, Dave, to do this?
Well, I mean, it can take seconds to an hour or something to get pretty reasonable answers.
Okay. And so that's the main vision here. So that's the outputs. Now let's go to our site descriptions, and we'll talk a little bit about that.
Okay, so we did the demonstration project here at the same site. This is the Naval Air Station Jacksonville. We were lucky enough to have two different distinct source areas within that site, within Operating Unit 3 that we were able to work in. So the left panel is just an aerial view of Building 106. It's actually the former Building 106. It used to sit right here in this empty space now. And that was a dry cleaner operated for several decades, from the 60s up until about 1990. So the primary constituents there are PCE and TCE. These purple circles here are our investigation points. We did 6 points here, 4 of which we then came back and did high-resolution coring in. So groundwater flow is from left to right on that on the source area number 1. So the right panel then is source area number 2. That was Building 780, and that's a former paint stripping solvent recycling facility that was thought to operate in the 70s and 80s. So the primary constituents there, and there is a typo on here, is PCE, TCE, and actually 111 TCA, and they were released to the aquifer there. And there were 4 investigation points here, and then we went back and did coring at 3 of them.
Okay, so Dave, my hypothesis was we're going to go to both of these sites, and at almost all 7 of these locations, we're going to go in here and do this analysis, and we're going to see these declining concentrations over time, right? So you're going to tell us if I was right. Mm-hmm.
Well, yeah, it's good to set up a hypothesis. It's good to test that hypothesis.
Okay, so we'll go through it, but the question is Chuck right or not?
Yeah, that's the question we ask ourselves every day.
A lot, right? Yeah. Exactly. Okay, so then we're on the next slide, and this is just some MIP data. So this is the y-axis is depth from ground surface, below ground surface, and then this MIP response we're doing as part of a companion CERTA project. We spent a lot of time experimenting with the MIP and different ways to get improved signals from low permeability zones in there. That's a different project, a different story. Here, this just shows that at this particular site, this location, we're looking at this example right in here that a lot of the mass of this contaminant is in this clay-rich low K zone. And so this is really where we're going to focus in here, use these different methods to identify exactly where these interfaces are, because this is an interface question. What's been flowing through the transmissive zone and what's loading up these clays? So that's what we're doing. So how do we figure out where that stuff is? Mm-hmm.
So for this, we used basically a multi-step approach where the first step was sort of a screening stage. In this case, we used both MIP and the Waterloo Advanced Profiling System for real-time delineation of low K zones and targeted groundwater sampling. The MIP is the data that we saw in the previous slide. The Waterloo Profiler allows you to get a hydraulic conductivity index. So it's sort of basically a surrogate for hydraulic conductivity, so you can see where those low K zones are, and you can also go in and collect groundwater samples from the more permeable regions. So it allows you to sort of identify those interfaces, identifies the target-rich zones to sample. And so you go back in on number 2, just basically saying core collection and subsampling, so getting a high-resolution core data from those low K zones in order to back calculate the source history. We're using fine spatial resolution and sample preservation in the field.
So we do this graphically. These are the different methods we had out here, and we used a lot of different methods to explore how they were, what information they gave them, and ease of use and things. But on the very left, we have the MIP that we used to analyze roughly where this contaminant was. We also did GeoProbe, this HPT device, to get continuous data on the hydraulics of the system. Then this water loop groundwater sampler that we looked at. Also, this water loop gave us some hydraulic index information too. And then moving over, we did this GeoProbe to get groundwater samples at different locations throughout this interval. And then we did the high-resolution soil coring on the right, up to 50 samples from this thing. And then this wasn't this really pure, it's all clay and it's all sand above. There was some transitions in there. So it did take some thinking about where the interface really was. Is that right? Mm-hmm.
Well, and it's one thing, to visually inspect a sample and say, well, this is where we think that the more permeable regions would be versus impermeable regions based on soil type. But some of these things will give you an actual K value that you can say, well, this is more or less where the permeable regions are. So it provides a backup for what you might see through just visual inspection or logging.
And then just more about soil coring. You want to show Steve Chapman's hockey elbow? What is it, high sticking or?
Oh, yeah.
Something about that. But who's on the picture here?
Yeah, so this is Steve Chapman. He doesn't like to see his face seen. I guess in this photo he's got his arm up. But what he's doing there is then extruding subsamples from these cores. Basically, in this case, we're trying to take samples pretty tight intervals, 2 to 12 inch intervals. I'd say on average we were going about every 6 inches in this case in order to get this detailed profile that we can use for our modeling. So we did 4 locations at building 106, that's a total of 298 samples, 3 locations at building 780, 166 soil subsamples, and these are all then preserved in methanol in the field. So our primary analytes in this case are the volatile organic chemicals in this case, but also we want to get fraction of organic carbon, physical properties. We did some additional analyses in terms of isotopes and biomarkers to get a handle on the extent of degradation we might expect in these cases too.
Okay, and just a little bit of foreshadowing, methanol, pretty important?
Pretty important.
Okay, let's go to the next slide and talks about, we're going to the actual sites themselves. Let's take a look at our profiles. We've got our 4 locations where sort of groundwater flow is from left to right. And you're looking at these, the dashed lines roughly are where we're saying this clay unit is. And let's look at that one on the left there, Dave. In the clay itself, it doesn't really look like a shark fin, right?
No, it really looks like a diffusion profile that's decreasing with depth.
Okay. But in each one of these 4, we compiled the data that's basically in that between the dashed lines, put that in the software tool to reconstruct the source history. So what does it look like once it gets in the tool? Mm-hmm.
Okay, so moving to the next slide, the left-hand side here shows that it reproduces that depth concentration with depth, and then these 2 right panels are showing the actual model output. So in each of these, the top one is the PCE, the second one is the PCE plus degradation product. So let's look at the top one first. The source history, the actual thing that we're trying to determine is the top part of that panel, and the core data is right below it. These little orange dots are the measured data, the data that you measured in the field, and then this solid line is basically the best fit line that's coming from the model prediction. And so if you look at this, we get a very good fit of the line, of the data with more or less a constant concentration versus time profile, starting back basically at 1962, more or less when we think that the releases started occurring.
Okay, so
and then on the bottom panel, we see the same basic pattern for the degradation products. At this particular location, there was almost no degradation to be seen.
Okay. And so in this case, looks like a constant source that went across here, right?
Yeah.
Well, maybe the next building, 780, is going to help me out. So here we've got our basically clay units where we found and looked at all the mass, and it looks like this stuff was this 5-foot interval of this clay that did have more of a shark fin in there. So almost visually, you can sort of think about the style of this thing before you do any analysis. Putting in the software, it's more likely to get some of this decay. So we're going to take the far left-hand panel and throw it into the software on the next slide.
Yeah, and just one other thing to highlight on this slide is that there's multiple contaminants here. We see chlorinated ethines and chlorinated ethanes. so it was a little bit more complicated of a picture. The next slide, slide 20, just looks at the case for the chlorinated ethene. So it's TCE on the top and TCE and its degradation products on the bottom. And lo and behold, we do have this shark fin type profile that is the best fit for both of these cases. So you see on this case, the concentration starts off high, decreases over time until it's basically nothing at the present day.
But you did this for other constituents too, right?
Right.
Okay. But I think we got a blow-up slide of that top part.
Okay.
Go on the next slide. Let's take a look at that. And so here is really this decaying source, so we're just blowing this up. We've got a source starting in 1971. Where did that thing come from? 1971. We had that from more historical data, or was that?
That was more or less, we knew that the presumed date when this facility was operating was the 70s and 80s.
And that seems to help out, right? If
Yeah.
you have some idea. Not totally necessary that you need this thing. But then it looked like we're seeing some signal potential from an excavation that occurred, quote, about 1990. We're seeing an SV pump and treat, which doesn't maybe seem to see a lot of the a big strong signal. But we're looking at milligram per liter on top. Goes from 30 in 1971 to 12 to 3, and then it's been fairly constant at 1 according to this thing right in here. So what about degradation? This was a big degradation story in that site, right?
Yeah, and this is one of the things we sort of added to our evaluation after the proposal phase. Somebody brought up that you need to have a handle on the amount of degradation that is potentially happening in the transmissive zone versus the low K zone, because the type of profiles that you would see could be definitely impacted by where that degradation is happening. So we did a fairly comprehensive evaluation at Building 106 for this, and two of the primary things we looked at were biomarkers, so the evidence of potentially degrading organisms, where we saw those. The data that we collected here was a little bit mixed because we had some basically inhibition going on in terms of expressing or amplification of the DNA that was extracted. There was evidence of dechlorination dechlorinators in the various layers at this site, along with vinyl chloride reductase, which did indicate that where dechlorinators were present, they were capable of dechlorinating all the way to ethene.
Okay, so some bugs in the clay, but not a lot, right?
Not a lot.
I mean, it didn't show up everywhere. So how about the isotopes? Let's take a look at that. It's on this next slide. And on this graph, you see the gray. This is the approximate boundaries of this low K unit. This is Building 106. The farther you go to the right, the more degradation you see. And in this case, we're looking at likely that there's more degradation in the upper and lower sands than we see in the clay itself. So this says maybe some degradation here, but maybe not a lot. Is that right?
Yeah, and I think the overall case with all the lines of evidence, we went through quite a few of these, including both, the patterns of where we saw parent versus daughter products, led us to basically have a pretty strong case that most of the degradation at this site is occurring in the transmissive zone and not in the low K zone.
Yeah, there's a lot of interest. The CERTA project that talked about, is there any degradation in low K zones? People have seen it in some sites. This one we're thinking maybe not so strong.
Yeah.
Okay.
So those are some of the initial results, and this next slide, slide 24, just basically in terms of our performance assessment for our objectives, how this worked is we're collecting that data, the high-res soil core data from the demonstration site. We're also using some data from sites that were published in the literature and using that to sort of test our tool, to validate the tool. We get these site-specific source history estimates, and then we evaluate them relative to our performance objectives. And so the first one that we're going to go through some of these data, in relation to those performance objectives. The first one being accuracy, and we looked at accuracy, with these metrics. But one other way to think of accuracy is just sort of, do the results make sense? Are they consistent with what we know or what we'd expect based on site conditions?
Did the plume arrive at a down gradient well after the ones in the up gradient? So some of that. So on the next slide, it talks about this Building 106. This is the dry cleaner site, the one with the constant concentrations, and we've got these different curves that you're looking at, the soil core data, and this isn't the one with the shark fin, but the more the exponential decline. And you can see that as you go down gradient, the source zone is the one on the left, down gradient is the one on the right, the penetration depth into these clays gets less. And Dave, that's just because that plume arrived there at a different time. And so I think the next picture really shows that, right, in terms of arrival time?
So slide 26, we're looking at those same output data, source history data, overlaid on the aerial of the site. So left to right is our moving down gradient, and you see these things basically arrive. Here's the source. You see that right away, 1962. Moving down gradient, the release date, or you move to an arrival date of 1971, 1976, 1980, with a decreasing concentration in each case, and less and less associated with that parent compound. So still a constant source, but attenuation along that flow pathway with sort of an arrival time that makes sense.
Okay, and then we had some monitoring well data. So the next one it talks about, on each one of these graphs is where the monitoring data shows up, and that's the points. What's the dashed line, Dave?
The dashed line is basically the predicted concentration based on our model.
So we aren't predicting here on months. This is more several-year clumps, right?
Correct.
That it's not a week or anything like this, but it is saying that we're getting close to certain of these different lines, and we thought that this was supporting evidence that this source history method is able to extract out this history. Mm-hmm. So next we're going to look at the next site, right?
Okay, so the next site, this is the building 780 source area, and instead of looking at multiple locations of the same site, we're going to look at multiple constituents at this same location. So this is the location closest to where we thought the release point is, the source area is. And we have TCE, 11 DCA, and 12 DCA at this. There wasn't actually any 111 TCA at this location. It all apparently been transformed to 11 DCA by the time we get here. We see slightly different patterns in each one of these. TCE and 12 DCA have those characteristic shark fin that's indicating of a decreasing source concentration with time, and so that's what we saw at those. 11 DCA is a pretty low concentration by that point and doesn't look like it penetrated or showed much attenuation at that.
Then we can look at the plume arrivals at building 780, and we do have this picture that as you go farther down gradient, these sources appear a little bit later. 1971 is where we see it right by the original source. 1973 right in here. 1976 is in here. Seemed to match there was wide ranges in the seepage velocities, right? But in the end, it was within some of the ranges that we saw in terms of the travel time and absorption and things like that. So overall, we said that these plume arrivals seem to make sense. So now we're going to go into the performance assessment itself, and were we accurate and precise and easy to use? Mm-hmm.
Yeah, and so these are data again from the building 106 source area. This is one location OU33. It's basically the nearest to the source. And one of the things that we were looking at in terms of performance is the relative percent difference between the actual data, these orange circles, and the model predicted data, which is basically the line. And on these for this instance, we saw pretty good agreement. We saw a median relative percent difference of 12% for PCE and 21% for PCE plus the degradation product.
So those two met this guideline.
Met the guideline that we had set up, which is a 30%.
This is building 780, the same sort of thing. Even with a shark fin, we're seeing more scatter on that one on the left. You know, it seems like the curve comes down a little bit too quick, but still, this is a RPD of this 20%, right? And it still matches our information. 7% on the right looks pretty good. But overall, what was the story when you lump all these guys together?
Well, overall, we didn't pass this metric that we'd set up, which is plus or minus 30%. We only made it for 7 of 17 source history estimates that we generated. We do like to point out that it did pass the eyeball test. I mean, the fit looked pretty good. The RPD might not have been, in hindsight, the best way to sort of try to look at this. You can get a pretty high RPD value from even when lines are not really that far away from the predictions. We set up an alternative metric where we're looking at it relative to this RMS error, relative mean square error, and we met it for that, so we felt like that was maybe a little bit more realistic metric.
I think some of this came from originally that some of the Beth Parker's work had some very smooth curves at that Connecticut site. Mm-hmm. Maybe stratigraphically it's more uniform or simple. And so we just saw this to scatter. You get a point at one location, go a little bit deeper, and it was just off to the side, and so that's the nature. So it didn't actually meet the criteria that we had assessed for accuracy, but certainly the conceptual model and things like that look pretty good. Next is that the model predictions are consistent with other source history methods. So we're looking at how our tool, we've applied this to a series of other sites, right? And it was...
Yeah, we went and dug through the literature. Some of these are sites that Beth Parker and Steve Chapman worked on before that got published data on them, 5 different sites or areas. We used 14 different locations, sort of take already available data and work it through our model and see what kind of answers that we got from that.
And so we used the blue and ball data, and we used some of these other data, and this seemed to fit and to work.
Yeah, it worked really well, and in these cases we can get answers pretty quick. We're not having to go through a numerical modeling exercise in order to set these sort of things.
So the whole tool part seemed to be, consistent and seemed to be workable. So how about the precision? This is performance assessment number 2.
So number 2, we're looking at precision. Basically, again, are you going to get the same answer if you go out and do this at the same location 2 different times? We went and took duplicate cores from one location, basically stepped off, half a meter to a meter, and had 2 side-by-side cores. We got sort of maybe we didn't necessarily know if we're going to get the same actual concentration versus depth data, but it was very similar, the data that we got. And so both the top and the bottom panel there show the source history estimates we got from those duplicate cores, and they were very, very similar. And so you get the same basic answer in this case.
Okay, so we got our chart from our actual original demo plan and everything else, looking at this performance objective. Can you get these same data from doing it twice? Do we get this RPD less than 30%? We passed all for 10 out of 10, right?
Yeah.
And then, so it seemed like that this seemed to work, and that this precision was, we passed that test.
Yeah.
Okay, next performance assessment number 3, sensitivity.
So looking at sensitivity,
are we sensitive?
Well, we like to consider ourselves so. In this case, this graph here then shows data from the tool itself, which has a Monte Carlo analysis built into it. So you can take a variety of different input parameters, and if you think you're highly certain of it, you could change it by plus or minus 10% and see how that impacts your results. If you're uncertain, maybe you're going to change it 50%. So you can do whatever you want to it and see how that particular parameter sensitivity might impact your results. So this one shows for porosity what would happen with a plus or minus 50% change in it. You see the blue lines then are all the different realizations that happen when you make a plus or minus change on that. And there is some slight difference in the amount of penetration you might get or the initial concentration, but the sort of take-home message with this is even by changing something plus or minus 50%, which is pretty big for porosity, you're going to get the same style of source history. You're going to get either the same basic shape of this curve, even with pretty high degree of uncertainty.
Okay, so there's this Monte Carlo routine where you can go in there and then change some of these input parameters, tortuosity, porosity, retardation, and it tells you what band you get in there. And if you wanted to, then you could take some of these different bands and see what source history that gives you, right?
Yeah, and you can do combinations of those parameters too. You don't have to just change a single parameter.
Okay, so in terms of our quantitative table assessment, we said looking through this that we were able to help quantify the sensitivity. There's this tool in there for people to visualize this and see how it goes. And so we said in these 2 cases that we thought this was useful. This did pass. It didn't have that much sensitivity to this to a lot of changes in this degradation half-life, and not that much to FOC, right? And so that's one of the things we learned from this, that maybe it's those are maybe certainly important, but maybe less important than some others. Okay, number 4, methods comparison.
Number 4 was just trying to take a look at how various things of how we were collecting the data impacted the type of data we got. And as Chuck mentioned earlier, it was sort of also a check to make sure that the way that we were getting our data, which was somewhat specific to how the University of Guelph has done these sorts of investigations, if you were going to be able to get comparable data without relying on sort of their lab or their techniques. And there is some take-home messages from a lot of these. We're just going to show a snapshot of sort of some of the data that came out of this. The left graph on here is showing basically on the y-axis, it's showing data from encore samplers, and the x-axis shows data from the basically the Guelph sampling device plus field preservation. And there is a definite bias in these Encore samplers, and the primary reason for this bias is we sort of used the method without using methanol preservation, and so we saw lower concentrations without methanol preservation. We saw a much higher degree of scatter in the data in that.
Dash line is the one-to-one?
The dash line in this case is the one-to-one. The solid is the actual slope of the regression line. So, a secondary thing with that is, well, say you didn't do the methanol preservation in the field. If you waited until you got to the lab, would that actually be a sufficient enough step? So the right-hand graph shows the impact of delaying that methanol preservation until it arrives at the lab. You see a little bit of an improvement in the data, higher R squared and a slightly higher slope, but it doesn't actually really address the data. So our main take-home message from this was really to emphasize the importance of immediate field preservation for collecting high-resolution data.
So to summarize in our chart here, we this top row where we said we failed, that's really because of this methanol, right? And
right.
You can fix that with the methanol itself, and so that's the middle row. And so the bottom one was just the duplicates. When we do duplicate samples, they seem to be pretty good. That passed there. So overall, that's the fourth method in terms of assessment. So there's forming technically how well it does, but then there's the cost piece, right?
Yeah, and so slide 40, this is the cost model that we built. Some of the elements are outlined here and whether we track those. This is sort of a different sort of project. So it was more of a characterization project than a treatment project, but these are the sort of things that you have the necessary steps in here, but it doesn't have any real materials or long-term monitoring, O&M type things. You're basically doing this investigation, getting data from modeling. Sort of that's the approach.
Just trying to capture certain elements of this method in here. And so we use these three scenarios, right? Mm-hmm. Mm-hmm. And the first is just implementation of source history approach is the standalone characterization approach. And the scenario 2 is this helps lead to M&A versus source treatment and then M&A, so we compared that. And then scenario 3 is source history leading to M&A versus pump and treat. So scenario 1 is just the source history approach, and scenario 2 is we're comparing it, the additional cost of source history compared to this approach. I'm not going to do this method, I'm just going to do an in situ bioremediation. And then scenario 3 is I'm not going to do the source history, I'm just going to put a pump and treat system in. Is that sort of close?
Yeah, so it's an outcome-based cost assessment.
Okay, so 3 scenarios, green, purple, blue. What were the results here?
Okay, so on this slide, basically, one is the cost with standalone source history method at a sort of similar scale site. We're talking about $160K, and so in this case, you're using that approach to get yourself data, maybe to support your site conceptual model, or just to provide you with more information about your site. Source history, then M&A. We're talking about a $650K operation over the scenario that we evaluated. Basically, 25% savings relative to not doing this approach, and then scenario 3 with source history with M&A compared to pump and treat. There's a pretty sizable cost savings of 75%, as you can imagine with this, if you can avoid going to a long-term pump and treat outcome for site management.
And so it's this idea that if you could, if it's something that's this line of evidence that helps avoid some of these active treatments, and in some ways this helps support some of the emerging things that are coming on in the business. Source attenuation, people are talking more about M&A for sources. That's in the new sort of BSTCP monograph that's coming out. The NRC report talks about transition assessments. If you can say that long-term this thing has been attenuating, I think that helps the idea that you can go to this passive long-term management. And then just the complex sites. An hour ago, I was on the complex site team for ITRC, and we're trying to come up with a checklist in various ways to assess when you transition assessment. And maybe information like this could be useful and give you more confidence. Hey, it's okay to go to this long-term management type approach. So here are these just cost drivers. So this is some of the cost data you've looked, and one question is how many how much does it cost to do this? And so on the left-hand panel, it says number of locations cored is on the x-axis, total costs in thousands of dollars are on there. So if you're doing 5 locations, then the total cost on that's a little under $200,000, and that's for this detailed coring, all the lab work, things of that nature. And then this cost per foot goes down like that. And then the right-hand panel is the soil sampling frequency. That's how many you do per foot.
Yeah.
And what,
in this case, it's feet per sample.
any recommendations, or what does this graph show? Mm-hmm.
Well, I think that we would prefer that you sample as frequently as possible. So in this slide, you'd be on the left, closer to the left of the x-axis. I think every 6 inches is really pretty important for getting a good profile, some confidence in that profile, because there can be some scatter in the data, as Chuck mentioned, due to small variations or heterogeneity in the soil type. So, so that's what we're trying to look at here, is the impact of that decision on the cost that you're going to end up with.
How about scale up? What's the story there?
There's not really any particular issues related to scale up. What we did with this project was try to do it at a sort of scale that would be similar to what you would do at any particular site. So we don't really foresee anything related to scale up that would be problematic. The sampling equipment is certainly all relatively available. You can get fairly high quality data with the commercial lab. We have some recommendations on ways to ensure high quality in the report, but I think that this is something that if somebody wanted to do right now at their site, they could readily do it.
So lessons learned, we think we can capture the style of source history and then actually get the semi-quantitative estimate of what the source history is. Some parameters are more difficult than others. We were tortured by tortuosity. It's sort of set up in different ways in different parts of the literature. We tried to clear it up, and the manual tells exactly what we think the bottom line is. Available tools and training?
Yeah, we worked really hard on getting this software tool so that it was sort of a valuable tool, but also very usable for people, and so we feel like we've succeeded with that. The tool is designed to be free for anybody who wants to use it. Right now it's available on our website, and as it gets finalized, it'll be available obviously on the ESTCP website as well. This detailed user's manual is also provided to accompany it, which provides a lot of guidance for how to apply this method and some tips for various ways of sort of evaluating your data as well.
We sort of trotted this out, different places: University Solvents Consortium, 2013, Battelle, NAS Jacksonville partnering meeting. It's sort of a fun presentation to give because you're looking back in time, and these arrival dates seem to work, so those have been well accepted. You've got 2 manuscripts, or we have 2 manuscripts in review, right?
Yeah, currently under review. There was also data from this project was used to support a groundwater paper that was already published. It was done jointly with the team for the sort of locate project as well.
So getting some papers out there.
And we have a lot of data, obviously, with this, and we'll probably submit 1 or 2 more manuscripts before we're done.
Okay, and then it's also got a little sort of text box or half a page in this new ITRC Dean Apple characterization guide. So I put this in there as sort of an emerging technique, and so the ESTCP's contribution to the science in there is displayed in this ITRC document. And with that, I think we're done, right? And 1 minute over, so not too bad, huh?
Thanks, Chuck. Thanks, Dave.
Oh, don't tell me.
I'm sorry. If you could still mute your phones if you don't have a question.
You told me now I can.
Some chatter in the background.
Good party going on.
Sorry about that, yeah.
Mm-hmm.
Are there any questions?
Hi, this is Marvin. Chuck, Dave, great presentation. This is less of a question and more of a comment. As you very well know, where CERTIP ESTCP is embarked on trying to expand our capabilities in outreach and in tech transfer. We're trying to do this through social media, and we have several vehicles that we're using, and we're trying to get over.
I'm gonna tell you what my guidance is. Always do one.
Thank you. I'd like to be there. They sound like they're having a lot of fun. We're trying to do it through social media. Andrea set up via Twitter, Facebook, and LinkedIn. Right now, I'm looking at LinkedIn as maybe a key vehicle to be doing this. The types of information that you have here on this project is likely going to be commented on and posted. I didn't see anybody from GSI. I would urge you folks to, both you, Dave, you and Chuck, to go back to your company and maybe discuss with some of your colleagues about getting involved on this, where for every time somebody gives a thumbs up on a particular project or the likes, it goes out to all your clients. You don't have to comment. You don't have to write blogs. Sometimes it just takes nothing more than the click of the mouse, and all of a sudden this information is going out to hundreds of people. We would urge you folks to please get involved in that.
Great. That's a great comment. And just a little bit of background is that when Andrea did send out this note, can you send us some information so ESTCP can put this information out? And so, Andrea, you got our text with all of our proposed text and graphics for the 4 media. Is that right? Mm-hmm.
Actually, I don't remember seeing that, Chuck.
Okay. It was a Word file. I'll make sure we send it. We sent it out maybe 2 weeks ago. So I'll make sure and send that out again. So we did it for all of our projects. So it's good to ask you about that. And the second piece is when I saw Andrea's email, I actually went into LinkedIn and started spending about 30 minutes on it, and then I made the vow I'm gonna really start engaging on it. But it was too complicated for that one sit down. I'm gonna have to dive in and really make it happen next time.
Yeah, I would urge you to
also.
Also.
On board with that is the bottom line. Very much on board.
Yeah.
Yeah, speak to the rest of the people in your company about it also. We're very excited about it. It looks like it has a whole lot of promise. And after, like you said, navigating for about another 15 or so minutes, you're going to realize just how great this the potential is here, okay?
Yeah, so I got to engage on that, and then definitely that's on my list. And then Andrew will make sure that you get the information for all of our projects, and we'll resend that today.
Okay, that'd be great.
Mm-hmm.
Any other questions for Chuck or David?
Well,
Okay.
This is Holland. If we got 2 seconds, it looks like. You all talked pretty quick. It was great stuff. I wonder if you comment at all about the spacing intervals and what value you get or don't, maybe even close to interfaces by going closer or not.
Mm-hmm.
Thought about that?
Yeah, you played around with this, and are there certain parts of the curve you were really trying to match near the interface and the peak?
Yeah,
right?
there's 3 places that are really important in terms of kind of matching that. That's the interface, basically the peak, and then the base. And the interface and the peak might be at different locations in that case. And for us, I mean, yeah, it always comes down to you want as much data as you can, so you'd like to recommend as close a spacing as you can. But sometimes cost comes into that. There are cases, I mean, just talking anecdotally with Steve Chapman about this, where they feel like they've sort of missed the peak or missed a big curve or something like that because they weren't sampling as frequently as they could, and that's just because they were coming into either really thin zones
mm-hmm.
or zones where there was just a high degree of heterogeneity. So I think that we've seen, in a lot of data that things can change pretty quickly within centimeters scales, and so doing something every foot, you sort of feel like you probably miss some important data. Mm-hmm. Doing everything every inch, you might be overkill at some sites.
And thanks. Hey, this really is good stuff, by the way.
Thanks.
Thanks.
Any other questions? Okay, Chuck, David, I just want to thank you for taking the time to provide this final debrief on your project. It really is valuable to us, and we really appreciate it. Thank you.